7.2 of course. Okay. All right, all these things. All right. So we finished that 5.3, 5.4 thing last time. We're going to do 5.5 and 5.6 in a day. Okay. And with these things, if you get practice, practice is a good thing. You get to learn this stuff. All right, 5.5, more properties. Properties of definite intervals. Okay, properties of definite intervals. All right. With indefinite intervals, it's pretty much like a derivative relationship, right? Okay. And we did already talk about two of them. All right. A, review. All right. And from this point on, we'll assume integrability. So in this class, the integral will always have a value in this class. In count 2, that might not be true. But in count 1, I'll at least give you the concession that, hey, these integrals will have a value. So we're going to assume integrability. We're going to assume integrability on these various intervals. It's going to work. Assume integrability. We'll practically take that for granted. By the way, what automatically gives us integrability? Continuity. That helps. Okay. Now, what's the general format for a definite interval? Well, the integral from a to b, f of x dx, or, g of t dt, whatever. Okay. Now, if a is less than b, all right, then we have a natural area interpretation. Okay. So if we go from x equals a to x equals b, and if the function is non-negative, then we associate the value of this definite integral with the what in this region? The area of this region. Okay, but we don't need units unless it's a general word problem with a context. Okay, but as this stands, there are no units. Okay. Now, what if the function does sometimes go negative? Or maybe it's entirely negative. What if we have something like this? Okay, we have something like this. Well, these regions contribute positive numbers to the value of that integral. This region contributes a negative value. So in this class, the value of that definite integral could be positive, could be 0, could be negative. Right? There will be some real quantity. It might be indicated by like a or b or something, but it would be a real quantity. All right. And sometimes we do have things like variables in there, and I don't even know if they're officially definite or not. If you fix the value, it is definite. Okay.
So the first part is if A is greater than B?
Okay, now, yeah, you're right that here we're assuming that B is greater than A. Okay. Although we're going to relax that in just a moment. We did mention this earlier. All right. Okay. So positive. Right. Any other questions? Any other questions? We associate values of definite integrals with a sum of signed areas. We associate the value of a definite integral with a sum of signed areas. Okay. All right. Now, we did talk about two properties earlier. Okay. First of all, the integral from c to c of f of x dx. All right. So we have the graph of y equals f of x. All right. What's the area of that line segment? 0. Right, 0. Okay. This assumes that f of c is defined, and that will be the case in this class. All right. So the integral of a function from a number to itself will be 0 in this class. All right. Second, we will talk about situations where the lower limit is greater than the upper limit. That can happen. Okay. And what property will help us in that regard? Well, the integral from b to a, f of x dx. Okay, how is this related to the integral from a to b of the same? So they're going to be opposites. Okay. Now, in terms of the underlying theory, what I'm going to tell you is that this will allow later properties to be consistent with our earlier properties. Okay, so this helps bring us consistency. All right. Okay. So we talked about that earlier. All right. We're going to talk about more properties now. Okay. And we'll see why it is this is very helpful. Okay. Issue B. All right. Well, we have this for limits. We have this for derivatives. We have what what property here is that L word? Linearity. Local, continuity, linearity. Okay. But I'm glad you remember that limits are local and derivatives correspond to local behaviors. All right. Integrals tend to be more ambitious. Okay, linearity. Okay, and this is a way that we split the integrand. How do we split the integrand? All right. Well, it's very similar to the way we split up limit problems and derivative problems. Okay, we love linearity. But this is what makes, now you might disagree, but this is what might make calculus easier than pre-calculus, right? Because in pre-calculus, the square root of a sum was not the sum of the square roots, generally speaking, right? Same thing for sine, cosine, logs, right? But hey, limits, derivatives, integrals, right? The limit of a sum was the sum of the limits. The derivative of a sum was the derivative. The derivative of a sum was the sum of the derivatives. Okay? Now the integral of a sum is the sum of the integrals. Alright. So, okay. You know, what does this mean? We can integrate term by term. Well, we mentioned this before, right? For indefinite integrals, we can integrate term by term, and constant factors pop out. We mentioned this way back in 5.1, right? With indefinite intervals. All right. Well, the same is true for definite intervals. And again, this is a way we can split up the integrand, the guy we're integrating. All right. So I'll do an example here. All right. Example given. Okay. Let's say I tell you that there's a function whose integral from 0 to 3. All right. F of x dx. Let's say it's 10. Take it on faith. Right. I'm your cult leader. I say this thing's 10. All right. And you all know. Okay. So, for example, you know, it might look like this. For example, here's x equals 0, x equals 3. Okay, maybe this area is 10. All right. Okay. That's sort of a visual there. After that. Okay. Now you're given this. Take it on faith. All right. Then, what can we say about the integral from 0 to 3 of 4 times f of x plus 1, all dx? So if you know this piece, then you should be able to figure this one out because of these properties of integrals. All right? Okay, first off, once again, the integral of a sum is the sum of the integrals, okay, if they exist, which they will. All right, so this is going to be the integral from 0 to 3, 4 times f of x dx, and don't forget to put your dx thing or whatever, your d whatever thing on all of these integrals. Dx, dt, d theta. Right? Okay, plus integral 0 to 3, 1 dx, and in fact the 1 there is optional. If 1 is the integrand, you don't even have to write it. Okay, so the integral of a sum is the sum of the integrals. All right. And then, what can I do with this constant factor here? Pop them out. All right, so the 4 on the outside, all right, 4, integral, 0 to 3, f of x dx, okay, plus, now, wait a minute, I should be able to figure this out from the geometric interpretation, right? Sometimes the geometry makes things very simple. If I wanted to graph y equals 1, how do you graph y equals 1? Horizontal line, yeah. So here's y equals 1, all right? We're going from x equals 0 to x equals 3. Come on, it's a rectangle. And what's its area? 3, right? Because the width is 3, the height is 1. So the area here is going to be 3. Okay? So I know that the value of this is going to be 3, just from the geometric argument. Okay, right. And this thing here, well, don't forget what I gave you. I'm telling you that's what? 10. I gave that to you. All right. 4 times 10 plus 3, that's 43. There's no word problem context, there's no unit. All right, 43. All right, just an application of properties of integrals. One benefit to this is that if you know how to integrate a basic guy like this, okay, if you know the value of a basic integral like this, you can build up related integrals. Right? Okay, questions? So for example, you know, maybe you know how to graph y equals f of x, you're not clear what this transformation looks like, this guy stretches, this guy translates, and it kind of makes sense, right? Okay, but you might not understand how this graphs, so if you understand this piece, you can figure out this piece computationally, not necessarily graphically. All right, questions? Building up these integrals. Remember, the answer to a definite integral problem is typically a number or something that represents a number. Okay. Should not have x in it though. Okay, now, the thing is, for a definite integral, we might consider splitting up the integrand here for f of x plus 1. But now, for a definite integral, we can also consider splitting up this interval, right? This interval from a to b, right? So how do we split the interval? That wasn't as much a concern for us back in the index days. Split the interval. All right. Well, here's the basic idea. Right? Okay, so I want the, okay, so here's A, here's C, here's B. All right? So let's say you have a piecewise function. And this property I mentioned is sometimes used for piecewise functions. All right? Maybe you have this like parabola thing, and then this linear thing. All right? Here's the graph of f, y equals f of x. Okay? And I want to know the value of this definite integral. All right? I want to know the value of the integral from a to b, f of x dx. But he might be a piecewise guy, right? Maybe his rule changes at c. Okay? So what am I going to do? I'm going to write this integral as a sum of two integrals. Okay. Although in a different way from this. Okay? We're going to integrate from a to, let's stop off at c. All right? Integral from a to c, f of x dx. Okay, that could be one rule, the parabolic rule, right? Plus the integral from what to what? C to d. Sorry, C to b. C to b. Bob, B as in Bob. F of x dx. Where f of x here would correspond to the linear rule over there. Okay? So if you have a piecewise guy, bear in mind, we are still continuous here. That's helpful. Although, you don't need continuity. You have integrability, it helps. But integral from a to c, da-da-da, plus integral from c to b, da-da-da. Although, it's a different rule here. Okay. So this integral corresponds to region 1, right? This region over here. This integral over here corresponds to region 2, like this guy over here. All right. And you agree that when we add those values up, we get the total area of this overall region. And by the way, this is the case even if the values are, positive, 0, or negative. Okay. Here I'm drawing them as though the values were positive, but they don't have to be positive. It's just nicer to illustrate that way. All right. Bottom line, one way to look at this, okay, if the upper limit of one integral, okay, is the same as the lower limit for another integral, and you have the same integrand, then you can basically fuse and merge these integrals together. Integral from a to b. Blah, blah, blah. Questions about that? Questions? I have a question. Does this work even if c is on the outside of that interval? And the answer is actually yes. If you still have, for example, continuity, right? Integrability. All right, it does still work. Okay, even if you have a situation like this, where a is here, b is here, and c is all the way out there. Okay, the properties still hold, even if c jumps over to the outside, as long as you still have integrability. All right, so here's an example. All right, example, simplify the following. All right, integral 9 to 5, f of x dx. Okay, integral from 9 to 5, f of x dx, plus integral from 3 to 9, f of x dx. All right. Okay. Now, if you want to make this look more like this template, okay, then it might be helpful to you to switch these, right? Switch the order of the terms. That might be helpful. So So let's go ahead and switch the order of the terms. Of course we can do that. Integral from 3 to 9, f of x dx, plus integral from 9 to 5, f of x dx. Okay. So again, that'll make this template look more like this template over here. Right? This will fit this template better. All right. You can see here that the upper limit for this guy matches with the lower limit for this guy. All right. They match up, and they have the same integrand, right? Okay. You still have f of x as the integrand. All right. So we can write this as the integral from what to what? 3 to 5 f of x dx. All right. Questions? Bear in mind, when I say that they have the same integrand, bear in mind that on different pieces of an interval, there might be a different expression. Okay, but still, it's f of x. All right, so the integral from 3 to 5, f of x dx. And that's pretty simple. That's pretty good. All right. Now you might ask the question, well, can we visualize this? I mean, what exactly is going on here? All right. Well, let me focus on this second line over here. Okay, I'll do a picture for this guy over here. All right. So let's say we have this sample graph. All right. X-axis. Okay, and we have this sample graph here. All right. Here's x equals 3. Here's x equals 5. And here's x equals 9. Okay. So what is the second line telling us to do, basically? The second line is telling us to take the entire area from x equals 3 to x equals 9. All right? So we take the entire area, okay, from x equals 3 to x equals 9. Now take a look at this piece here. All right? The integral from 9 to 5 f of x dx. Now you might be thinking, that sounds weird. I don't know how to visualize that. Well, how can I rewrite that? How can I rewrite the integral from 9 to 5? The opposite of what? The opposite of the integral from 5 to 9 f of x dx. And of course you know the interpretation for this, right? That's the area of the region between x equals 9 and x equals 9 under the curve. F is non-negative, so it's a straight interpretation, all right? But what are we doing here? We're subtracting it. What does that mean? We're basically deleting it, right? We're then cutting this off. Well, what are we left with? Right? The integral from 3 to 5. Makes sense. Makes sense visually.
But what you're not doing is subtracting it from, never mind.
So you take the entire region and you're subtracting off you take the area of the entire region, you subtract off the area of that region to the right. You then get the area of the region to the left. So visually this should make sense.
Well, yeah, when I was beginning to ask the question, for some reason I thought it was the first integral was at 3 to 5.
Oh, no, I'm going from here to here.
Yeah, it makes sense when I look at it.
Yeah. Okay. Yeah, here it's kind of confusing from here. It's easier to look at it from here. Right? And bear in mind, f could be positive in value. It could be sometimes 0. It could be negative in value. Sometimes or all the time. Okay. So even though it's convenient to draw f as a non-negative or positive value function, it could also be negative value sometimes, and these properties still hold. Okay. As long as we have integrability, okay, meaning that these have values, and they will in this class. Later on in Calc 2, you will talk about an integral, they're called improper integrals, where you have a discontinuity and you wonder if they converge or diverge, kind of like a series almost, right? So that's an issue for Calc 2. Sometimes you do have a value. Even if you have a VA and you try to integrate over the VA, the discontinuity, sometimes you still get a value. Depends how fast the graph is approaching the VA. All right, that's an issue in Calc 2. All right. Questions? By the way, in Calc 2, you really have to know your pre-calc and your Calc 1. In Calc 3, you have to know your Calc 1 and pre-calc. And maybe a few techniques from Calc 2. All right. Next, inequalities. Okay, and these are fairly straightforward. Okay. Inequality preserving rules. I'm kind of making that phrase up. But the basic principle is fairly straightforward. Okay, inequality preserving rules. Okay, fancy terms for some fairly basic principles. Okay. And in Calculus 2, it's a big issue of of, what's bigger than what. The idea of an inequality, what's bigger than what. All right. So, for example, okay. On interval. Okay. So let's say we're talking about the closed interval from A to B. Okay. And when I say on, I mean throughout. When we say on an interval, we mean throughout the interval. Okay. On the closed interval from A to B. Okay. First of all, number one, or I. Okay. I. All right. Okay. If f of x is non-negative in value, okay, on or throughout that interval. All right. So we have something like this. Okay, here's A, here's B. Okay, the graph of f never falls below the x-axis. Okay. Well, guess what? Then the integral from A to B, from A to B though, from A to B, f of x dx is also non-negative. And by the way, when I write something like this, it's implicitly assumed that b is greater than a. Okay, that's implicitly assumed here. Right. If b were less than a, that would be the empty set. Okay, so if the function is non-negative on the closed interval, then the corresponding value of the definite integral from a to b in that order will be non-negative. Of course, the integral from b to a would then be non-positive. All right. Now here, we're comparing the function value to 0. Right? If the function value always beats 0, maybe high 0, but if the function value always beats 0, then the corresponding integral will beat 0. All right. But what if we compare f of x to g of x, some general guy, not necessarily 0? All right. So 2, this is more general, and this subsumes that. All right. What if we have a situation like this? Okay, here's A, here's B. Okay, here's f. The graph of f, or y equals f of x, right? And here's the graph of g, y equals g of x. Right, here's the graph of g. Well, guess what? The integral for f is going to basically beat the integral for g. Right? And that's the case regardless of whether f and g are non-negative, or maybe they're both negative in value. Right? If both these guys are below the x-axis. All right, that's cool. Okay, basically the graph of f never falls below the graph of g. Okay, and in that sense, it doesn't matter where the x-axis is, right? These can be positive or negative in value, whatever. All right. If f of x basically beats g of x, or could top, right? If f of x is greater than or equal to g of x on the interval, meaning throughout the closed interval from a to b, then what can we say? The value of the integral from a to b, f of x dx, will be greater than or equal to the what? The value of the integral from a to b of g of x dx. All right. So basically, if this function beats that function, his integral will beat this guy's integral. Okay. Or we assume again that b is greater than a. All right. So here you could say that non-negativity is preserved. Okay. So here, non-negativity is preserved. Okay. Over here, I use the word dominance in my notes, although I used it in a different context in chapter 2 when we talked about limits. Here, the lead is preserved. What? The lead is preserved. I used dominance back in chapter 2. All right. So if this guy's leading, his integral's leading. But once again, case 1, it's kind of like Rawls' theorem, right? Case 1, this is just a special case where the g function is 0. All right? We're comparing f to 0. Here we're comparing f to g. All right. Okay, questions? Questions? As a practical matter, this is useful, right? If you know a function is non-negative, if integral here is non-negative, I think this is one you use more often. Right? You'll see that more. Okay, questions? Questions? All right. Now, on that test, I know you had fun with the mean value theorem for derivatives, right? So what are you going to ask me? Is there a mean value theorem for value theorem, the MVT, for definite integrals. Now, is this the most valuable theorem? Well, he's important, or she's important, in its own right, okay? In the sense that it's not that you actively apply it as a student in calculus, but it's a key tool in proofs, in theory, and it helps to link the pre-calc ideas and make them calculus ideas in the limit. All right. So it is in the background, like the Wizard of Oz. Okay. I was going to make a James Franco joke, but then if it's a videotape, I'm going to get burned by the James Franco fans. All right. Okay, mean value theorem for definite intervals. And by the way, there's a related idea here which you might find more helpful. We're also going to define FAV. Okay, and what's FAV? In fact, we're going to define this first. Okay, we're going to define this first. All right, FAV, technically on an interval. Okay, so again, we're specifying a closed interval from A to B. When I write that, we assume that A is less than B. Right? FAV on the closed interval from A to B. That's going to be the average value of F. This is the average value of F, okay, on that interval. Okay, the average value of F on that interval. Okay, and I'm going to build this up. So you might want to jot this down because my notes are rather concise on this. I want to develop this idea of average because I want to give you the idea of why this makes sense. In my notes, I'm a little quick. All right, so let me flesh this out a little bit more. Okay, so first of all, graphically and conceptually, how would we think of the average value of a function? All right. Now, in basic statistics, basic discrete statistics, it's very straightforward. Okay. So let's say I have like a bar chart. All right. Let's have a bar chart. Okay. Here we have 6. Here we have 7. Here we have 8, and these all have width 1. All right. Okay. Now, what is the average of 6, 7, and 8? It's 7. Now, what's one way of looking at that? Take a block from here, right? That top block from there. Stick it over here. And what can I do? If I play Legos like this, what can I do? I can arrange to get a rectangle. I can basically, move stuff around so I get this rectangle of height 7. Okay. So this idea that the average value, okay, corresponds to the height of the rectangle that you get if everything's leveled off. Okay. If we live in a communist society, everything's leveled off. Okay. 7, 7, 7, right? 7, 7, 7. All right. And that will be the average value for these three. So in discrete statistics, that's very straightforward. But the problem is that in calculus, we're dealing with functions that are curvy, right? They don't have flat tops like that. They're curvy. So it's kind of it's trickier to give them haircuts, right? Okay. So yeah, because they're curvy. So how do we deal with that? How do we define average value? Let's start by doing that. Okay. Let's go ahead and start by doing that. Okay. So let's say that we have axis. All right. Let's say we have a graph for a function that looks like this. So here's the graph of f. Y equals f of x. All right. Here's A. Here's B. And again, folks, we don't need the property that f be non-negative, but it's convenient for visual purposes, right? Okay. All right. So let's say that's the graph of a function f from x equals A to x equals B. All right. It's a bit trickier than that because this guy is curvy, right? He's always changing, right? He's very curvy. All right. So how do we give this guy a haircut? What's going on here? Well, you agree that these have the same area, right? The goal is to retain the same area here. Well, what would be the area of this piano? The area is given by what? The integral, the definite integral from A to B of f of x dx, right? And you agree that corresponds to the area here. Okay. Again, we don't require that f be non-negative. This is true in general. Well, then it would be interpreted as the sum of sine elements. All right. Now, what's the idea? X-axis, y-axis. Now, how do I define the average value of f on this interval? Okay, and although we should areas are equal, or the sum of sine areas. All right? Okay, so what's the idea? This definite integral, which represents the area here, equals, okay, well, what do we want it to be? What's the width here? It's going to be b minus a, right? Okay, it's going to be b minus a. And what's the height, the sine height? Well, we want to be the FF, the average value of the function, which again could be positive, 0, or negative. Clearly here in this example, it'll be positive. Let's solve for FF. Okay, what would be a logical definition for FF on the interval? Well, we're going to define the average value on that interval as the integral, definite integral, from a to b, fx dx, all over b minus a, which we know is not 0. Okay, here's positive. All right, and you agree, that seems like a reasonable definition, right? Basically, you know, the sine height is going to be the sine area divided by the width, right? Sine height equals sine area over the width. Remember, if this block is below the x-axis, for example, you have a negative number. Right? Okay, questions about that? Questions? And why does this make a lot of sense just looking at the discrete case? Okay, well, if you use a formula, how would you use a formula to work out the average? It would be 6 plus 7 plus 8, all divided by 3, right? Like if I average your test scores, I take the sum of all the numbers, divide by the number of numbers, like n. Okay? Over here, it's a very similar flavor if you think about it, right? Because an integral, we often do think as a kind of continuous sum, right? Because what is a definite integral? We defined it last time as a limit of whose sums? Mr. Riemann sums. Yeah, limit of Riemann sums. Okay. So the integral is like a continuous summation, all right? Over, this is like an input size, right? Okay, that's like an input size. All right. This width, this bandwidth on the x-axis. All right. So this does follow that general theme, right? It's a sum, it's like a continuous sum in this case, over like an input size, kind of similar flavor, right? It makes sense. Okay, so do know this. All right. And that is an interesting definition in and of itself. What is the average value of a function on an interval? All right. Bear in mind, we usually do assume continuity, in which case we automatically have a value for that. We don't exist. We don't exist. Questions? Questions? Know that. Okay, that's how we define average value of a function, even if we have continuously changing function on an interval. All right. In a way, it's an extension of that. Okay, you'll accept this. Now, so that was a big spiel just to establish what an average value is. Okay. Now, what does the mean value theorem say? All right. Well, first of all, I'm going to make you look back, make you review the mean value theorem for derivatives, which of course you know because you've taken the test in chapter 4. So you know this. All right. The mean value theorem for derivatives. Now, the bottom line is, I'll make it simpler. Okay. The bottom line is, if a function is nice, right? At least on the interval. If a function is nice, okay, what's the deal? I'm focusing more on the conclusion here. All right. So we have the graph of function f. All right. Okay, here's A, here's B. And we assume that the function is nice, so it has appropriate, so it's continuous on the closed interval, differentiable on the open interval. Okay, fine, it's nice. What does that mean? We're guaranteed that there, was that key E word? There exists. Key word there, exists. I really wanted to see that in your definition. There exists. And we're not guaranteeing uniqueness. I'm not saying it's unique, but there does exist a C in here, let's say. Now I got to pinpoint this. All right. Okay. There exists a C in here. There may be more than one, right? C1, C2. I got two. All right. But there does exist a value of C in the open interval from A to B, such that if you interpret it geometrically, all right, the tangent lines at those points are going to be parallel to the what? The secant line. Okay, from x equals A to x equals B. All right. So the MVT for derivatives posits the existence of tangent lines, at least one, that was parallel to the secant line. I do know that in the test, I wanted you to be more existed a value for x in here, perhaps more than one, perhaps, where the instantaneous rate of change of f equaled the what? The average rate of change of f. I'm going to write that because that's how we link. All right, that's where the link is. What did the MBT for derivatives say? It said that there existed a c value, okay, in the open interval, okay, such that the instantaneous rate of change of f, okay, equals the average rate of change of f on the interval. Okay? There's at least one place in here where the instantaneous rate of change equals the average rate of change. And once again, folks, this is a link between pre-calc and calculus. Average rate of change is a pre-calc concept. Your pre-calc class should have covered this. I know mine did. All right. Instantaneous rate of change, that's a creature of calculus. That's derivatives. That's tangent lines. Okay? Okay, so remember, you agree. That's what the mean value theorem for derivatives said graphically, okay, and also in terms of rates of change. Right? In a way, the mean value theorem for integrals is even more fundamental. Okay, and we do see this sometimes. Sometimes it seems like we're asking the more obvious questions later. This does happen sometimes in calculus. Okay, so what's the more fundamental question? All right, the mean value theorem for definite integrals. All right, now conceptually, what is this going to say? And then we'll state it more formally. All right, let's say we have this function again. That's nice. Although, as it turns out, we don't even need differentiability. The only requirement is continuity. Okay? We don't even need differentiability. You could have a corner. Okay. Now, here's A. Here's B. All right. Now, what does the MBT for definite integrals say? It says that if f is nice, in this case that means continuity. All right. It means that there exists. Now, Sokowski uses z for some reason, just because it's a different letter. All right. There exists a z value in the open interval from A to B. All right, maybe over here. Okay. There could be more than one. Although this guy is 1 to 1 here, so there are no other values in z, but there could be. There exists a value for z in the open interval from A to B, such that, okay, it's not this rate of change stuff, such that the function value, such that the function value, an even more basic concept, the function value equals the, I put average here, I mixed words, average, I was mixing words there, okay, equals the, what, the average, or, yeah, the average, not the average rate, the average function value, the average function value. Average function value, f(f), okay, on that interval, okay, on the closed interval from A to B. Technically, the z is in the open interval. Okay, so over here, back with the MBT for derivatives, we're talking rates of change, right? Relating an instantaneous rate of change with the average rate of change. Here, we're back to function values, right? That's an even more basic concept, right? There exists a z in there, an x-coordinate, z, where the function value equals the average function value. That's an even more basic idea, right? But the reason why we add it later is because this requires integrals. And practically all calculus textbooks put integrals after derivatives. It would be a very rare one that did. Okay. So more basic idea, but we needed integrals, right? We needed an integral to define what f(f) was, all right? By the way, graphically, what do I mean by that? All right. So this guy here, I'm claiming that there exists a z in here, such that if you draw the corresponding rectangle, okay, it's going to correspond to the same value for its definite integral. Here we can think in terms of areas. The area under the white curve will equal the area under the yellow line segment, the area of that yellow rectangle. If f is sometimes negative, it's more subtle, but you know, same basic idea. Yeah.
So you're saying z can't be A or B?
Technically, no. Technically, no. And in fact, stronger in that sense, in the sense that we know that there's a guy strictly in the interior of A and B that does that. Coincidentally, sure, it might be true at A, it might be true at B, you know, if this guy curls around, right? But there exists a guy in here, and it doesn't have to be A or B. We know there's a guy strictly in the interior where that's true. It is true that when you're working out the problem that we're going to do, right, when you're working out problems to find out what values for Z are going to work, technically you would knock out A or B. Although on an exam, if you fail to do something like that, I'm not going to penalize you. All right. Okay, questions about that? Questions? Are we ready to see the actual theorem? I mean, this is a lot of it, right? But here's the actual theorem. All right. Here is the MVT for definite integrals. And I could ask this, you've seen this, I could ask something like this on the test, your quiz or the final. Your quiz and or the final. Okay? You have this on your sheet of notes. For the final. Part 2. If you do that, that's on your own time. That's your private space. All right. So what is the MVT for definite integrals? All right. The theorem. What does the theorem say? All right. If F is, there's only one requirement. Continuity. You don't even need differentiability, just need continuity. If F is continuous on the closed interval from A to B, then, okay, well, just like over here, it's an existence theorem, right? Not uniqueness, existence. Then there exists a Z. Of course, you can use any letter you want. Don't use A or B again, right? But Sulkowski uses Z, so I use Z. Then there exists a Z in the open interval from A to B. On the test, if you write closed, I won't penalize you for that, but technically we can say open. There exists a Z in the open interval from A to B, such that this next statement is very straightforward. If anything, this was very drawn out. Such that the function value there, f of Z, equals what? FF. Okay, on that closed interval. All right. So it really is more compact than the one for derivatives. The only reason why it's later is that we needed an integral to define what FF was. Okay? So if F is continuous on the closed interval from A to B, then there exists a Z in the open interval from A to B, such that f of Z equals FF. In my notes, I kind of blend the ideas together, but this is, I think, a better, more sort of spread out presentation of this. All right, questions? Questions? We do hit the average function value somewhere in here. Okay, we do hit the average function value somewhere in here. Maybe more than once if this guy's not 1 to 1. All right, questions? Questions? And in fact, before I even go into the homework examples, you might be wondering, well, so what? I mean, here I gave you the speed example. You can kind of see how this can be applied. Where does this come up? Actually, this does come up very importantly in the theory of definite integrals, because, like I said, these are used to bridge pre-calc and calc. They're really important in a theory sense. Okay. Let me give you an example why. I'm going to connect this to what we did last time. All right. Remember Riemann sums. Right? Remember Riemann sums. That's how we define these definite integrals. Right. Here's the idea. So let's say you have a function f. All right. You don't know it that well. You're going to use a Riemann approximation. All right. Here's A. Here's B. Okay. We then get a partition or a mesh. All right. Let's say it's about regular. All right. We can do a. In this case, we can do a left-hand Riemann. Right. Okay. In this case, I'm doing a left-hand Riemann sum. Okay. But you agree, I could do a left-hand Riemann approximation. I could do right-hand. What else did we do? Midpoint. Okay. We could average the left-hand and right-hand. That turns out to be the trapezoidal rule, which we'll talk about next Monday. But here's what the MVT for definite integrals actually gives us. One consequence of that is the following notion. All right. You agree that, okay, we have a continuous curve here, right? You agree that there is a value for the definite integral from A to B, right? There is a value for this guy. Okay, our challenge is, how do we approximate that? What the MVT for definite integrals concludes for us, effectively, is that if you make an appropriate selection, an appropriate sequence of selections in these subintervals and you draw the corresponding rectangles, there is a way to get the exact area. In other words, remember when we did Riemann sums? In principle, you could stand anywhere within a given subinterval. It could be the left endpoint, right endpoint, midpoint. Mathematically, it does random. Stand random. What this theorem says is that there is a sequence of selections from these subintervals where if you do the rectangles, you do get the exact answer. But how do you get that sequence? It doesn't tell you that. All right. But there does exist a sequence where it does work out. Now, one other consequence is if we let the norm of the partitions approach 0 when we make finer and finer partitions, basically, it's like in the long run, in the limit, it doesn't really matter where you stand. Whether it's left endpoint, right endpoint, midpoint, whatever, we're going to converge to a limit, and that's going to be the exact area. Okay, that's all a consequence of this, really. Okay, it's a key one. Questions? Questions? There is a way to get the exact area. The problem is we don't know exactly how to do it. Where exactly do we stand? But this says that there exists, again, there exists a sequence of selections of places where we stand where we would get the exact answer. And that's true whatever position we use.
When you say the limit, do you mean like the long run?
Well, I mean that when we consider finer and finer partitions, and we let the norms of these partitions approach 0, that means the widest width approaches 0, right? Okay, that means that regardless of where you stand, left endpoint, right endpoint, midpoint, okay, you're going to approach the exact value for this guy. Whether you're using left hands or right hands or midpoints or randoms, okay? And in fact, this theorem says that however you split the interval up, there is always a sequence of places where you could stand where you would, in principle, get the exact area. The problem is that we usually don't know where those places are. but such a sequence does exist.
Can you explain again why you don't want to make the number of rectangles so
Oh, well, why it's not sufficient? Now, for a regular partition, that's sufficient, all right? The problem is that if you just say, hey, just let the number of rectangles approach infinity, well, then what if you have something like this? You have this guy here, and then you have this guy here. What if you just break things up over here, and you leave this guy just standing there, right? Well, we're letting the number of subintervals, n, approach infinity, but we're not going to get the right answer. We're not getting this piece over here. See, this is a stronger condition that forces this guy to break up. We need this guy to break up. This guy forces him to break up. This guy doesn't. Again, for a regular partition, that's sufficient. Questions? Questions? All right. So that's the link. All right. Again, it's a theory link that bridges pre-calc and calc. All right. See here on this subinterval. Look at this one subinterval. What the mean variance theorem for definite intervals is saying is, if you stand here and you draw the rectangle, this rectangle will work for this subinterval. See what I'm saying? Okay. And this principle applies to other subintervals as well. Okay. If this is like from x0 to x1, right? Then x1 to x2, and so forth. Okay. Let's do an example. Example number 26. Because I know some of you are going, wait a minute, we haven't seen too many like homework type problems, right? Like crunching. Okay. It's not all crunching, but it's a relief. All right. Given the integral from -1 to 3 of 3x squared minus 2x plus 3 dx equals 32. Now, of course, as good critical thinkers, what question would you like to ask me right now? Well, how did I get this? Aren't you asking that? Well, how did I get this? That's 5.6. So Sokowski is acting kind of backwards, and I do think it's a reasonable approach. He's giving you the properties first, and then telling you how to actually evaluate these long things. Well, he wants to introduce the properties first. Right now, take it on faith. Now, you might argue, well, hey, you're not the boss. Well, actually, I am, but it's not mine. But for right now, you're going to take it on faith. You're going to take it on faith for now. Okay, the value of this definite integral is positive 32. Now, if you're skeptical, hey, when we do 5.6, that's the second half of the class, you're going to want to stick around. Obviously, you're going to want to stick around for the fundamental theorem of calculus, right? Obviously. So you're going to see, how we evaluate this 32. I'll give you a hint. We're going to need indefinite integrals. Okay, it involves an antiderivative. That's how those two get linked together. All right. All right. Okay, so let's let f of x be this. Remember, for an integral problem here, we normally let f of x be the integrand of the guy we're given, a little f of x. All right. And let's see. Now, actually, Sokowski's part B, I'm going to need to do as part A. This is number 26 from Sokowski's set. I'm going to do as part B first. So first, this is part B. We're going to find FF on this interval. Okay, we're going to find the average value of f on the closed interval from -1 to 3. All right. Well, we should know the formula for that. Okay, so FF. And bear in mind, I'm not always going to write that interval. Technically, we should indicate it, but I'll just write FF. We know what the interval is. FF is, okay, what goes in the numerator? It's the
32.
yeah, you're right. 32 is the interval, right? It's the interval. -1 to 3 of f of x dx. All right. So, interval from -1 to 3, f of x dx. That's that guy, right? Over, well, b minus a, that's 3 minus -1, right? Okay. Right, this is b minus a. All right, this is the integral from a to b. F of x dx. Maybe I should have done this first, right? That's how we define it. Right, and then a is -1, b is 3. Okay, I'm just plugging in. Right. Okay, I gave you this was 32, right? Over 4. What's the average value? 8. Okay, no units. I don't have a word problem setting here. All right, so the average value is 8. Okay, now just for your benefit, of course you don't typically have to do this, but let's graph this out, see what's going on here. All right. X-axis, right. By the way, what's the graph of y equals f of x? It's quadratic. Parabola. Parabola being up. All right. Now again, you typically won't have to graph this to this level of detail. Here's -1, here's 3. The vertex is barely in quadrant 1. All right. It turns out to look like this. Something like that. Yeah, okay, something like that. All right. Okay, now, the integral from -1 to 3, okay, that's this white area over here. And by the way, I'm claiming that what is the area of that region? 32, that's my claim. And well, you can prove that using 5-6 methods. All right, now, what are we doing here? In a way, we're finding a rectangle, right? Okay, so here's the rectangle. It's going to be height 8. All right. And it turns out to be this guy. If they happen to connect here, we'll talk about that. All right. But bottom line, my claim is that this rectangle I have in yellow. Okay. My claim is that that yellow rectangle will have the same what? The same area as the white shaded region. Again, that interpretation is convenient because everything's non-negative here. Although, the theorem works in general. It's just that when things are non-negative, it's clearer to see what's going on. But it does generalize to other cases. All right. Well, let's talk more about the conclusion of the MVT. All right. What does the MVT suggest that we do? Find a value for x where the function value equals 8. Average function value. Yeah. All right. Second, let's talk about the MVT for definite intervals. All right. So first, we're just talking about average value. What is the average value of the function on that interval? Now let's talk about the MVT. First of all, does the MVT apply? Do you agree that this guy's continuous?
Yes.
On the interval? Yes, of course. Polynomial, right? Okay, so f is continuous on the closed interval from -1 to 3. That's evidence of polynomial, right? Therefore, the mean value theorem for definite integrals applies. It applies. The hypothesis holds, therefore the conclusion must hold. Something exists. There's something that exists. Okay, what does the mean value theorem say? It says, as its conclusion, there exists a z-value, okay, in the open interval, technically, -1 to 3. If you say value, you put x too, there exists a z value in the open interval from -1 to 3, such that, okay, f of z equals f half on the closed interval, and we know that that's 8. All right. What's the obvious follow-up? Fine. Such values for z, that'll work. We know at least one value here will work. There may be others. And in fact, judging from the graph here, there is only one. Remember, this guy's not going to count. All right. Oh, okay. All right. That's x. All right. So let's find all such z. Find all such z. All right. So we're going to find the values for z that will satisfy the conclusion of the mean value here. All right. Well, very straightforward. Solve. You can use x or z. It doesn't really matter to me. We can use z. You can use x, that's fine. All right, so we're going to solve f of z equals 8. Okay, I want to know where the function value is 8, the average function value. Okay, so now I'll write the rule here. Instead of x, I'll write z. Again, that's not a huge deal. 3z squared. By the way, why am I crossing my z's? So they don't look like 2's. When I talk calc 3, that was actually a serious issue. A lot of people are messing up their z's and their 2's. That's why I always cross my z's now. All right. Okay, and then I also curl my t's, right? So not plus signs. 3z squared minus 2z plus 3 equals 8. All right. Should I factor now? No. What should I isolate on one side? 0. A lot of people forget to do that. Okay, remember, we want to isolate 0 on one side. If we're solving a non-trivial quadratic, when I say that, I mean there's a z term in there. All right. Otherwise, you might use the square root method. But we want to isolate 0 on one side. Subtract 8. A lot of people forget to do that. 3z squared minus 2z is going to be minus 5 equals 0. All right. If it comes down to it, you can use the quadratic formula. Turns out here factoring will work. You can factor all the integers, I should say. All right. So it factors as, okay, we have 3z here, z here, right? It's going to be a 5 here and a 1 here. It's going to be a plus minus, right? Yeah, be careful. Okay, 3z minus 5 and z plus 1. All right. Oh, equals 0. Okay, don't forget to write the other side. Equals 0. Therefore, by the zero factor property, z equals 5/3. Okay, or z equals -1. Now, this is a bit subtle. Comments. Do I take both? Technically, no. Technically, I knock off the -1. Now, on an exam, if you fail to do that, will I penalize you? I won't, but technically, we knock off the -1. All right. Okay, z equals 5/3. Is this in the interval? 1 2/3? Yes, it is. It better be. I mean, if that number's not in there, we're in trouble, right? We have to have some candidate. 5/3. That's the only one.
Professor,
Yeah, huh?
did you knock it off because it was negative, or is it because it's the end?
I knocked it off because it was A, and that's an open interval. Again, on a test, that's very subtle. If you take both, I'm happy you have to. Right. But technically, it's the open interval. And by the way, guess what? That corresponds to this intersection point. Here's 5/3. Right? It's the value for x or z, such that the function value, its y coordinate, right, is 8. Notice here, the function value here is also 8, but that's A. That's the left-hand point. We technically exclude it. So it's really only this point we're looking at. So that's the point where we raise the bar such that if you draw the corresponding rectangle, they'll have the same area as that white shaded region does. Right. So that's where we achieve the average value. First problem was to find the average value. Then the second problem was find out where we take on the average value. Again, similar to the MVT for derivatives, but that dealt with rates of change.
It's safe to say that we will commonly have like a endpoint.
No, actually, this was bad luck. Or maybe good luck, just to point out, technically we kill him, but, on a test, don't freak out. I would penalize you. But in a way, it's kind of bad luck that, yeah, it so happened that A was a potential candidate, but then we had to knock him off. Don't worry too much about it. Now, certainly, if you get like 10 or -15, yeah, knock him off. I'll be mad. I don't know if I'll be emotionally angry, but I will penalize you. I'm not gonna go. outside. 50 is not the interval. Take it out. Don't you know 50 is bigger than 3? All right. That reminds me of that the Naked Gun, 2.5, where George Kennedy wants to beat up the criminal, and the criminal beats him up. You see him on the floor. All right. Okay, questions. It seems like questions. We defined average value, talked about the MBT, other properties. Good time for a break. Come back. We're going to talk about the FTC. Fundamental theorem of calculus. How we get the value from the closed interval from A to B. Now, it's possible that F might still be integrable, but then we could not use the fundamental theorem of calculus, at least not directly. All right. In Calc 2, there are ways of kind of playing with this. Now, first of all, I want to go back to the old example. Remember the inheritance example we did back in 5.1? Okay, and I want to explain to you how we can relate that to a definite integral problem. All right. Do I look good? All right. Okay. Old example, 5.1. Okay. Next time you see me, I'm from the Hunger Games. All right. I inherit $1,000. Okay. I inherit $1,000. Okay. I'm just repeating. I'm repeating the same setup we had when we started chapter 5. All right. My same spending rate. All right. After T years. Right. And this is always changing. It's non-constant. After T years, I spend at the rate of $10T per year. Okay. So, for example, well, I'm accelerating my spending. After 1 year, I'm spending at $10 per year. After 2 years, $20 per year. After 2.5 years, $25 per year. So my rate of spending is always changing over time. All right, until I run out of money, which is about 14 years. I'm really stretching that out. All right. When you see rate, you're thinking what word? Derivative. You're thinking derivative. Okay. Although here, the idea is that you're basically being given information about a derivative, and you're going to do what I word. You're going to integrate. All right, and that's going to be a key thing. Now, when we did this in 5.1, we used an indefinite integral to model a function first, the amount we had remaining. You could also model it as the amount spent. All right. But you can also think of it in terms of a definite integral. We're going to link these two together. All right. First of all, let's review how we would have done it back in 5.1. How would we have done it back in 5.1? All right. And I'm going to ask a different question, actually. Before I ask, how long was it until we ran out of money? The question I'm going to ask now is, how much do I spend? How much do I spend from T equals 5 to T equals 6 years? Okay, after the inheritance. All right. How much do I spend from T equals 5 to T equals 6 years? So between the 5-year mark and the 6-year mark. Right. Okay, so that's within the 6th year, right? Because 0 to 1 is within the first year. So from 5 to 6, it's within the 6th year. All right. Okay, so how much do I spend? Question mark. All right. Now, first of all, I'm going to show you how you would have done this back in 5.1 without definite intervals. How would you do this using indefinite intervals? All right, so the old 5.1 method. Okay, the old 5.1 method. How do we do this? Okay, now, even though I'm talking spending here, I'm going to model an amount remaining. Okay, let f of t equal the amount of money in dollars remaining after t years. Okay, so it's the amount of money remaining out of my inheritance. All right, just to make this point, okay? Then that means that f prime of t is going to be what? I'm giving you the rate of change, but be careful. What is the derivative here? It's not 10t, it's what? Negative 10t. Why is it negative 10t? because we're spending and the function is being modeled as the amount you have remaining. Now again, you could have another function, g of t, let's say, that's the amount spent. Okay, but here I'm kind of pointing out this trick. Be careful, okay? I want to frame it like this to remind you, hey, sometimes you do want a negative sign. All right? If you're spending, the amount you have is declining. All right. And we have an initial condition. We're going to solve this differential equation, right? We're going to solve this differential equation subject to, or such that, okay, what's the initial condition here? I inherit $1,000. Parse that using notation. What of what is what?
F of 0 equals 1,000.
That's right. F of 0 is 1,000. F of 0 is 1,000. Okay. If you want, you can stick the unit here, right? This is dollars. This here would be dollars per year. Okay. All right. If you want to be a stickler. All right. Okay. So we're going to solve that diffy q subject to or such that that initial condition is true. It's a first order differential equation. We typically only need one initial condition. All right. Folks, we did this back in 5.1. All right. So I'm not going to repeat all that work, right? So again, look back at your 5.1 notes. All right. What do? We integrated both sides with respect to t. Okay. And we got a plus c over there, right? That helped us out with the plus c part. Okay. Back in 5.1, we found that little f of t, okay, was given by negative 5t squared plus 1,000. Or if you wish, 1,000 minus 5t squared. Okay, remember, that's the function that models the amount of money we have remaining after t years. At least until we run out of money. Okay, now that domain issue we talked about last month. It took us about 14 years. All right. So now let's talk about this. Okay, if we were to graph this function, y equals f of t, what's the graph of that? Parabola opening which way? Down. All right. So here's t. Here's y equals f of t. All right. The y-intercept is 1,000. F of 0 is 1,000. Okay. Of course, the model is irrelevant over here, right? Negative values for t make no sense here. Okay. And again, my spending is accelerating with time. All right. And then it stops here unless I'm willing to go to debt. All right. So I want this piece of the parabola. Okay. Maybe it extends. It doesn't matter. But I want at least that piece of the parabola. Okay? Now, what's the deal? Now, this is not to scale. Remember, we found out that this here was about 14 years. Okay, this is not to scale, but, okay, now here's t equals 5, here's t equals 6, not to scale, all right? So that here, the function value, the y-coordinate here, is the amount you have left in your account at t equals 5. This is the amount in your account at t equals 6. So what gives me the amount that I've spent? It's basically the difference here, right? Okay, we're going down by how much? The amount in our account is drained by how much? Okay, and that basically gives you the answer, right? This drop. Okay, so this corresponds to the answer. Okay, how much have I spent to get from here down to here? All right. Okay, well, if we know this this function that models the amount we have in our account, that's our account statement basically. What do? Well, the answer is going to be f of 6, the amount of money we have at time 6, what? Minus f of 5, right? It's like you take your bank statement. It's your bank statement at time t equals 6. You subtract off, remember, it's always new minus old, right? Change is new minus old, right? So it's your bank statement at time t equals 6 minus your bank statement at time t equals 5, right? It's new minus old. Okay. And then how would we compute this? All right. Again, this is the change in your money, right? The change in your dollar amount, the change in your money. Okay. And how do we compute this? All right, bracket. Okay, well, we plug in 6, right? We have negative 5 times 6 squared plus 1,000. All right. Minus brackets. Don't forget your brackets here. Okay. Whenever you're subtracting something with more than one term, don't forget your grouping symbols. What do you do here? Plug in 5. So let me reiterate what we're doing. We're taking this antiderivative, we're plugging in 6, we're plugging in 5, subtract the results, right? We're gonna see this a lot. Okay? Now what happens if we work this out? We're gonna get negative 5 times 6 squared plus 1,000, okay, plus very interesting. What's next? Minus 1,000. And what can I do here? Yeah, this is very nice. But you know, we should have expected this. Okay, why is that? I'm giving you the spending rate. Okay? Now, do you agree that regardless of what you inherited, whether it's $1,000, $10,000, $100,000, as long as you haven't spent it in 6 years, right? Whatever you inherited, $1,000, $10,000, $100,000, okay? If I give you the spending rate, you agree that the amount that you spend, okay, is going to be the same regardless of how much you inherited, right? Okay? If I give you the spending rate, right, then you're going to have the same amount of spending regardless of how much you inherited, right? Okay? Because these are two kind of separate issues, right? Now, you're strategizing, that's your finances, that's different, but, okay? But if I give you the spending rate, right, the rate of change, or the rate of change of your account, right, and this is negative 10T, okay, you agree. You will have spent a certain amount of money regardless of the initial condition. Bottom line, I know we talked about solving for C last time. In the end, if you're answering this kind of problem, did C matter? No, that's the bottom line. C is not going to matter. And a big smile should appear on your face. Okay? Because you're not going to have to worry about C when you do definite integrals. Okay? That's a key theme. Don't worry about C. The C is irrelevant. You may as well have taken the antiderivative where this was 0. Okay? May as well. That's an important point. By the way, when you work this out, you know, you get negative 55. How come this is negative? Because you're spending it, right? So what does it mean? You spent. I spent $55. Okay. From T equals 5 to 5 to T equals 6 years. All right. So I spent $55. Based on that rate, I mean, that rate is sufficient. I didn't need the initial condition. That rate statement is sufficient. Okay? All right, I spent $55. Questions? You could have answered this question solely using 5.1 method. But don't you agree that this seems like too much work, right? You agree that we might be able to streamline this, right? Make it more efficient. Let's do it. And we can do it using a definite interval. All right. First of all, we're going to employ a shift in notation. Okay, there's a notation shift. All right. So we go from 5.1 to 5.6. Okay, there's a shift in notation. All right. Now before, in 5.1, okay, the idea is that you're given f prime, all right, and then you're trying to find out something about f. Okay, you're given f prime, and you're trying to find out something about f. Okay. Now in 5.6, okay, the thing you're given as your integrand, we like to call f, right? F is your integrand, all right? And then the antiderivative corresponds to capital F, all right? So with the 5.1 method, we were going from little f prime to little f. In 5.6, we're going from little f to big F. Okay, so we're kind of shifting over the notations by 1. It's like, here's f, it's like, grandpa, pa, and you, right? There's little f prime, there's little f, there's big F. We're kind of shifting things over notation-wise. Okay. The idea is that this typically corresponds to the integrand. Right? This corresponds to the integrand. All right, it's like the thing you're given. All right. So now, here's how we're going to model it using 5.6. Let f of t, all right, this is going to be the rate. Let f of t be negative 10t dollars per year. Okay, that's the rate, right? The rate at which your account, the rate at which your account is changing. The rate at which your account is changing. Okay. And implicitly, if you want to, maybe write it. Oh, well, we'll be writing here. Okay. Big F of t, okay, is the amount in your account. The amount remaining after t years. The amount remaining after t years. So big F of t here takes on the role of little f of t over there. All right. We're giving you little f of t, which is negative 10t So what's the idea here? What principle are we going to appeal to here? All right. Okay, here's sort of a side example. Let's say that we're graphing velocity against time. Let's say you're driving a car. You drive your car at a constant rate of 50 miles per hour. By the way, this is not my notes, so you might want to jot this down just as an explanation. You're driving your car at 50 miles per hour. You drive for 2 hours. Okay? How much does your position change by? How much have you traveled? 50 miles per hour, 2 hours, 100 miles. That's the area. You all agree? That's the change in this guy's antiderivative, right? This represents the change in S of t, the change in your position, right? If you're going due north on the freeway, right? You're going 50 miles per hour for 2 hours, right? You're going 50 miles per hour for 2 hours, okay? Then your position is changing by 100 miles, okay? So what's the idea here? If you integrate a rate function, you're getting the accumulated change in his antiderivative, okay? That's the basic idea. I'll state that when I draw this out. So what's going on here? We're integrating a rate function. Okay, so here, we're integrating a rate function. There's a reason why I'm raising this up. T and little f of t. Little f of t is negative 10t. How do you graph y equals negative 10t? What is that? It's a line that is sloping downward. Okay, different scales here. All right, what's a line sloping downward? Right. So here's the rate function. All right. Here's t equals 5. Here's t equals 6. All right. T equals 5. T equals 6. Look at this sort of trapezoidal strip here. Look at this strip here. Okay. What is that strip? That strip basically gives us the answer. Okay. This represents the sort of net or accumulated change in the big daddy F, in big F of t. And this effectively gives us our answer. It effectively gives us our answer. Okay? Once again, when you integrate a rate function, you're getting the accumulated change in the big daddy. Similar to this example over here. All right? And of course, this region is below the t-axis. That indicates that our answer is negative. That indicates that we're decreasing, or our account is decreasing. All right. Questions? Question. How do we indicate signed areas in calculus? We use a. How do we indicate a signed area? An integral. What kind of integral? A definite integral with numbers. Those are the limits of integration, 5 and 6. Let's do it. So how did you solve this problem in 5-6, practically speaking? All right. Let's evaluate the following definite intervals. Evaluate means, simplify, find the answer. The definite interval from 5 to 6 of f of t dt. By the way, these better be t values. Okay, the limits of integration have to correspond to this variable. When we do u subs, that's going to be a huge issue. We'll talk about that. All right. Bottom line, we want to evaluate this. You agree this will basically give us the answer. Maybe the negative sign. Okay. Let's do it. So what are the steps? How do we evaluate this definite interval? All right. Now, when we did the 5-1 method, what do we do? You got the rate function, and what did you do to it? What did you do to it? You integrated it, right? Okay. So your first step is to find an antiderivative. Okay. So, okay. First of all, let me write this out. 5 to 6, negative 10t dt. First off, I'm writing out what little f of t is. All right. Now here, I'll make some comments here. All right. You want to find an antiderivative. Okay, find an antiderivative. Okay. And we normally put that in brackets. All right. Well, the negative t pops out. Integrate itself out anyway, where you have the plus c and the minus c, whatever c is. Okay, so, you know what, I think I'm actually going to switch my 2 and 3, but, well, I'm not. You don't need the plus c. You don't need the plus c, because again, whatever c is going to end up being canceled out anyway. All right, that's my number 3 comment. All right. And my number 2 comment. All right. Remember what we did before. Look, mechanically speaking, what do? We took the antiderivative. We didn't need the constant of integration. All right. And what do? We plugged in the 6. We plugged in the 5. And what did we do with the results? We subtracted them. Right. Okay. So the answer is given by. The answer is given. Okay. Big F of 6 minus big F of 5. Remember, the antiderivative is big F. Okay, the antiderivative is big F. All right, big F of 6 minus big F of 5. All right, so here's what we do. We plug in 5. Okay, negative 5 times 6. I'm sorry, 6. 6. Negative 5 times 6 squared. These numbers can go together. Sorry. Okay, negative 5 times 6 squared. Okay, minus, and then what do? Plug in 5. Guess what? Well, we've seen this before, right? When you work this out, you're going to get negative 55. The interpretation of the negative sign being that the accumulated change is negative because we're spending, right? Our amount in the account is going down. So once again, I spend $55. I spend $55, between time t equals 5 and t equals 6 years. All right. Do you buy that? Do you buy that? The plus c didn't matter. That should make you happy. So what is FTC? Okay, issue B. What is the FTC? Technically, this is FTC Part 2. Part 1 we'll mention later. Even though Part 1 is used to prove Part 2, Part 1 isn't as interesting, but I will mention it at the end. He's worth a mention. He could appear in your test. Right? But Part 2 is by far the most important. So much like Star Trek, it's Part 2 that we like to focus on more so than Part 1. Okay. And Godfather maybe. Okay. This is very short. This is the shortest one of all. I told you about the fundamental theorem of arithmetic and algebra. FTC Part 2. This is the shortest one of all. Here's what it says. Again, we're assuming continuity, right? We're assuming continuity. The integral from a to b of x dx equals, all right, what do? We find an antiderivative for little f. Guess what? That's 5, 1, and 5, 2, right? You're doing an indefinite integral, right? Okay, this is an antiderivative. Okay, use 5, 1 and 5, 2 to get it. All right? So using sections 5, 1 and 5, 2, find an antiderivative. As you might suspect, this is the hardest part of the problem. All right? The rest is really trivial. Okay? From A to B. And what is this? What does this mean? Well, you plug in B, you plug in A, subtract the results. Bottom line, this is that. In a way, it's the shortest theorem of all. If you have continuity, the integral from A to B, f of x dx, is cap f of b minus cap f of a, where cap f is an antiderivative. The plus c doesn't matter. Any questions?
Lowercase f?
These are lower, okay, now this is lowercase. These are uppercases. These are antiderivatives. You plug into the antiderivative, the negative pi t squared. You plug into the antiderivative. Please remember that. Not a mistake. Okay, don't plug into the integrand. Plug into the antiderivative. Okay, that's the guy in the brackets. And that's what this means. Cap f of b minus cap f of a. Remember, you evaluate at the upper limit, minus, and then evaluate at the lower limit. Okay, new minus old. Okay, I know that we say the integral from a to b, but you plug in b first. I know that's confusing. You integrate from a to b, but you plug in b first. In a way, the way it's written kind of hints at that. Okay, we say it's the integral from a to b. This does kind of hint that b gets plugged in first, though. And by the way, this is the case even if b is less than a. If you're integrating from 5 to 3, fine. 3 goes here, 5 goes there. Fine. So this works even if b is less than a. evaluate this thing. All right. Let's evaluate definite integrals. So why was it that name was 32, for example? Right? All right, example. And you're going to do a bunch of these, trust me. All right. Evaluate the following. The algebra here is going to get people. Evaluate the definite integral from 1 to 2. Fine. X to the fifth plus 7. Or x to the third dx. Don't forget your dx. And by the way, since this guy is non-negative on that interval, and it's from lesser to greater, you can interpret this as an area problem directly. First of all, observe that this is continuous on the interval. Okay, in this class, that goes without saying. Okay, because the FTC requires that. All right. So we have continuity, good. We can apply the FTC. The question is, can we find an antiderivative? That's the hard part. Can we find an antiderivative? I hope you can. Hey, if you don't, we try to approximate this using what? Using whose sums? Riemann sums, yeah. See? So I give you some hideous thing, you can't work the algebra out, try a Riemann sum. All right, but that's for an approximation, that won't give you the exact answer. All right, algebra. What do you think? Break it. What do you think I mean by break it? Split it. Yeah. Would you parentheses? X to the fifth plus x to the third plus 7 over x to the third all dx. You can do that if the plus sign's up there. You can't do it if the plus sign's down there. But you can split to the numerator. All right? Questions? Let's simplify this. Questions? Integral 1 to 2. What's x to the fifth over x to the third? X to the second plus 7 times. All right. 1 over x to the third, I'm going to want to write that in a power form. X to the negative 3 dx. I prefer this when we apply the power rule for integration. So you see, for the time being, we're doing an indefinite interval, right? It's like we're doing an indefinite interval. These limits will come in later on. We're still tagging along. All right. Equals, we're ready to actually integrate. Okay, I like to put brackets here. All right, from 1 to 2. All right. Okay, integrate. X to the second. X to the third over 3. Plus 7 times. Careful. Integrate x to the negative 3. X to the what? Negative 2. You're adding 1. Over negative 2. Remember, you're adding 1. Don't think about, are you going away or closer to 0? It's add 1. All right? You add 1. I don't care if we're getting closer to 0. All right. Let's clean this up a bit. All right. X cubed over 3. Okay, how about minus fraction? All right. The 7 is on top. Okay. 2 is on the bottom. Who else can go on the bottom? X squared. All right. From 1 to 2. Remember, you got to plug these numbers in, so it's to your benefit to make this kind of nice. All right. X cubed over 3 minus 7 over 2x squared. That's an antiderivative. Do I need the plus c? No, I don't. It's not wrong, but just avoid it. It's just confusing. All right. From 1 to 2. All right. So this is my big F of x. You don't have to write this, but that is my antiderivative where c is 0. All right. Let's continue applying the FTC. We found an antiderivative, a cap F. What do I do now? Cap F of 2. What do I do? Plug in 2. Okay, I'll put it in brackets for good measure. 2 cubed over 3 minus 7 over 2 times 2 squared. Okay? Minus, don't forget your brackets. What do I do here? Plug in 1. That's cap F of 1. Okay, you don't have to write this. If it helps, fine, but you don't have to write these. Write these, though. Okay? Partial credit. 1 cubed over 3 minus 7 over 2 times 1 squared. Conceptually, it's not that bad. The hardest part is find an antiderivative. And then it's just be careful. Plug in B, plug in A, subtract the results. Remember grouping symbols. All right? I trust you to do that. Let me check to make sure this is correct. Okay, when you work this out, you get the magic fraction of 119 over 24. All right, great. Okay, question?
Arrow. Do you use those? Like, what's the point of the arrow?
The arrows are there You don't have to write those. Those are reminders to you to put those brackets. Because a lot of people forget them and they blow a sign. You don't want to blow a sign. Okay. You really should use them if you're subtracting something with more than one term. Anything else? Anything else? Yeah.
I understand everything you're doing. I'm just for some reason having a hard time relating this back to like little f and f prime.
Okay, this is little f of x. I'm basically giving you the integram, right? When I give you a problem like this, you're given the integram. And in the new 5-6 notation, we call this guy little f of x. He represents a radian, right? This little f of x. In the process, when you work out the indefinite integral, basically, you're finding big f of x, an antiderivative. Now, bear in mind, when you work these problems out, whether you call them little f, big F, you know what? It doesn't really matter when you're working a problem. Just be consistent. I don't object. If you want to call him little f prime, then call him little f. That's fine.
Okay, it's just notation.
Yeah, it's just notation. Be aware that sometimes the book or I might shift. Instead of f and f prime, we might have big F and little f. Okay. Just be aware of that shift in notation. If you read a book or something. Okay, but when you work with these problems, it doesn't really matter. Find an antiderivative. I don't care what you call it. Yeah. Okay, and then plug into the antiderivative. Okay, you know what? A lot of people forget to integrate. They forget to find an antiderivative. They're so relieved that they get a nice form, and then they start plugging numbers. No, you got to integrate. Okay, maybe we should do that. Integrate. Put two big arrows here. Integrate. You actually do want to integrate. Okay, so you can see here, this is the step where basically you're doing an indefinite integration, right? When you find an antiderivative, you're basically doing an indefinite integral, except you don't need the plus c. Okay, so that's how 5.1 and 5.2 get wrapped into this. Here, 5.1. All right. Questions? Symmetry is your friend. Okay, I know you are sometimes irritated when I keep asking you, is this even, is this odd? But that can help you work out problems. In Calc 3, you can work out 2 triple integrals instead of 4. Trust me, this is a good thing. All right, you like symmetry. All right, example. Evaluate. We're going to evaluate. Integral, negative pi to pi. And you might be smelling something here. Integral, negative pi to pi of x squared plus cosine of x dx. We have more than one term with grouping symbols. All right. Okay. This here, little f of x, he is what? Even, right? If you replace x with his opposite, he doesn't care. Same value, right? This is even. Okay. Now, what does that mean? It means that, now you don't have to graph this, right? But if you were to graph this, the graph will be symmetrical about the what? The y-axis, yeah. Now, you have to do this, right? But it turns out the graph looks like this. It is like a smiley face, on that interval at least. Okay. From negative pi to pi. All right. And this will be non-negative also, all right? So in fact, the value of that definite integral will in fact be the region, the area of the region from here to here, all right? Now, here's the thing. When we do the FTC, at some point, we're going to need to plug in negative pi, at least as it stands. Now, you agree that we are very nervous about plugging in negative pi. Wouldn't you agree? That makes us a little nervous. Well, how can I rewrite this problem? Instead of integrating from negative pi to pi, why not integrate from what to pi? How about 0? Okay, take this area and do what? Double down. You agree that'll work. If we have symmetry, this will work. And you agree that plugging in 0 is usually more comforting than plugging in negative pi. I would agree with that. All right? So what's the deal here? We're going to write this as twice the integral from 0 to pi, okay, of the same, x squared plus cosine x dx. Okay, apply symmetry. Okay. Bear in mind, this trick works if these are opposites. Right? If that were like negative 2 pi, then this trick would not work. All right. Well, let's go ahead. So quickly, let's go on. All right. We have the 2. Don't forget the 2. All right. Big brackets. All right. From 0 to pi. Okay. Integrate x squared. X cubed over 3. Okay. Careful, folks. Whose derivative is cosine x?
Negative sign or
Plus. Check. Guess and check. Whose derivative is cosine x? Sine of x. Focus on the derivatives. Come on, man. What? parentheses. We might need them. All right, we might. Okay, the 2 applies to everything. What do?
Plug it in.
Plug in what? Pi. Plug in pi first. Pi cubed over 3 plus sine of pi. Minus, and then do what?
Zero.
Plug in 0. Wait a minute. If you plug in 0, what do we get?
Zero.
Yeah, you can see quickly, we're gonna get 0. Okay, and of course, in the end it won't matter, but still check it. Right? Oh, and by the way, what's sine of pi? Hey, that's 0 also. Hey, I love this. 2 pi cubed over 3. Beautiful. 2 pi cubed over 3. You get lovely results. All right, 2 pi cubed over 3. And the area here is 2 pi cubed over 3, what? Square units, maybe square meters if they were meters, right? Whereas if we had plugged in negative pi, you might be scratching your heads a bit. Right.
So
Yeah,
on the test, just when, since this all is coming together, are you gonna have us just find the antiderivative of something? Are you gonna say use a u sub on it, or are we just gonna have to look at it and think to ourselves?
you should be prepared to recognize when you need to use that.
Okay.
Yeah, yeah. That's a skill you need to develop. Yeah. A good point. You need to know when you need to do a use up. And by the way, we're going to do that in just a moment. In fact, I would say that's one of the problems that a lot of people fail to get correctly. Fail to complete all the way, and we'll see why. In general, how can the even property help you? If f is even, again, we're always assuming continuity. If f is even, okay, if f is even and continuous, all right, if f is even and continuous on the closed interval from opposite of a to a, of course I'm assuming a is positive, all right, then, okay, the integral from opposite of a to a, f of x dx, how can this be rewritten? As twice the integral from 0 to a of f of x dx. Okay. Or you could go negative a to 0, but that tends to be harder. Okay. 2 times the integral 0 to a f of x dx. And that makes it usually easier because we like 0 more than opposite of a usually. All right, questions about that? That's to help you. And in fact, I can ask you a short theory question, and you need to use that property. I often ask these little 2, 3-point theory questions. If this is that, what's that? Well, f is even, da-da-da. But you know what's even better? If f is what? If f is odd, then that can be really beautiful. Example, integral, negative pi to pi, x plus sine of x dx. All right, guess what? F of x is odd. You replace x with its opposite, you end up with the opposite. All right. Now again, you don't have to graph this, but here's the principle. The graph of an odd function is symmetric about the what? The origin. Turns out it looks like this. Here's negative pi, here's pi. Well, looky here. When you have this kind of symmetry, in fact, I don't care what the shape looks like, right? We have continuity, but I don't care what the shape looks like. If we have symmetry about the origin, and if these are opposites, what is your answer going to be? It's going to be 0. Look, whatever this contribution is, this knocks it out. All right? It's a tug of war, right? Answer is 0. So what if this is like cosecant to the 11th x? Okay, at this time, you may not know how to integrate it, but wait a minute. Hold on. Oops, not continuous on there. Yeah. How about sine to the 11th x? Sorry. So, integral of sine to the 11th x. We'll give it here. 0. You don't have to know the antiderivative. Hint, if you see an integrand and you really don't know the antiderivative, or you don't think you'll be able to find it, check to see, is it odd? If it's odd, and if these are opposites, and you have continuity, you're in business. All right. Again, I won't mess with you in the continuity sense.
Better be answer only on the test.
Yeah, that'd be like 2, 3 points. Yeah, answer only. 0. I might ask why. F is odd. F is odd. Integrand is odd. All right. So what's the general rule? All right. It's even better. find a guy who's of something that's odd and continuous on an interval, 0. Bear in mind, even if these are switched, it's still 0, right? Because the opposite of 0 is 0. All right. Good news, bad news. Good news, we have 2 more things to do. You know the bad news. All right. Questions? Questions? What is a problem that not very few, but few students get perfectly? And you really should do this because it's a student learning outcome, right? How do you evaluate a definite integral when you have to do a U sub? And people routinely mess up their notation on these things, and as a result, they often get the wrong answer. But if you're careful, okay, then you should be able to get good notation and the right answer. Okay, and I do grade on form. If you mess up the notation, I can mark you off even if you get the right answer. All right, example. What if there's a U sub, and you have to be very careful? All right, watch your notation. Okay, this is number 28 from Sokowski. 0 to integral 0 to 4, x over the square root of x squared plus 9, all dx. All right. I'll show you 2 ways to do this. The first way is more standard. Okay. In the beginning, okay, we think a U sub's going to work. This is not basic, and I don't see a good way of splitting that. You can't split it. All right. So let U equal. Let's let U be an inside guy. We'll make that nicer, and his derivative is basically in there, up to a constant factor. Let U be what? X squared plus 9. So I can make this entire radicand U. I'll make it nicer. We'd like to avoid a double sum. Not wrong, but we prefer one sum. All right. Then du is, what's du? 2x. Don't forget dx. Don't forget that. I do mark off on form. Forget that. All right. Du equals 2x dx. That's differential form. That's standard. In America. All right. Well, there's a kill-bill method. You can solve for x dx. That's half du. I actually follow that. X dx is half du, and that works. All right. I think compensation is one that is very popular. Okay. But there are a couple of things that we have to do. All right. First of all, we are in the process of going from x to u. There's something that has to change. For the first time, we're going to have to change the what? We're going to go to du, right? What are we going to have to change?
The interval.
Right? Yeah, you're right. The limits of integration. Right, okay. The limits of integration. The limits of integration, right? Well, directly we relate this to these 2 limits, right? And we associate an interval with them. Okay. All right. So we need new limits of integration. Okay. By the way, this is not limit as in chapter 2 limit. It's what we call those numbers. Okay. These are new limits of integration. Okay. And they're for u. Okay. They're for u, not x. So remember, the d blah, that blah is the variable that these are related to. Okay. In this case, these are x values. But we're going to need u values later. All right. So if x is 0, what's u? Here's a function, right? U equals x squared plus 9. That's how we get these things. All right? So u is x squared plus 9. U equals 0 squared plus 9. That means u is 9. All right? These are functions, right? If x is 0, u is a number. It's 9. All right? If x is what? 4? U is, well, 4 squared plus 9. That's 25. U is 25. And they go in the corresponding order. Okay? Now, folks, sometimes when you find the new limits, sometimes the greater number is here, the lesser number is there. That's okay. They have to correspond. Okay? So zeros guy, some people say u of 0. U of 0 goes here. U of 4 goes here. Okay? It's okay if this number is greater. Okay, don't switch the order just because you feel like it. Okay? You have to correspond. All right. That's one thing. Second thing, let's set this up. Let's start by compensating. Okay, so this integral over here, I'll star it. Okay. Okay, this integral, I'm going to set them up. I'm going to set up the compensation. All right, integral, 0 to 4, we're still doing dx. All right, fraction, x over, notice I'm moving them over, x over root x squared plus 9 dx. Right now, I'm just rewriting it. It would be great shouldn't be mixing x and u in the same integral. Let's go to u. Ready? Ready? All right, let's go to u. The 1/2 we keep. Integral from 9 to 25, right. Again, once again, if it turns out this number is greater than that, that's okay. You have to correspond. Okay, you have to correspond. Okay, all this stuff, 2x dx becomes du over what? The square root of u. Okay, and you agree that's an integral entirely in u? As far as you're concerned, I may as well have given you this. Okay, I may as well have given you this. Any questions? By the way, you remember how in 5.2 you went back to x? Do not do that here. Okay, you're just going to mess yourselves up. Like I said, you may as well have been given this. Don't go back to x. Don't look back. All right? Don't look back. Don't look back. Don't go back to x. As far as we're concerned, we're given this. If you try to go back to x, you will routinely mess up your notation and your answer. Okay, so forget him. We're over there. Don't erase this, but as far as we're concerned, we start there. Full new ballgame. Any questions? At this point, same old, same old. Big deal, different letter. Okay, 1/2 integral 9 to 25. And by the way, for some of you, to remind yourselves, it might even help to do this. If you write u equals 9, u equals 25. Okay, just to remind yourselves. But remember that if you don't have a label, these numbers are assumed to correspond to that variable. And that's one reason why we don't mix variables in the same integral. Because we know what kinds of values we're talking about. They're u values